Okay, so the following topic is not on your test, but you should see it. 6.7 is on harmonic motion. I don't recall why they call it harmonic motion, but it is. Harmonic motion follows an oscillation or wave. A simple example would be if I start with a mass hanging from a coiled spring. And this is in the neutral position. And I'll call that step A. And then it's pulled down. Capital B and A. It's pulled down this distance right here. That's going to be my amplitude. Let's say it's 10 centimeters. Pulled down. And then released. The spring will go back up to the neutral position. I'll call that C. And then it's got momentum, so it's gonna compress the spring a little bit. Go up to D. Then the spring is compressed so much that it pushes it back out. And it gets back down to E. And it keeps going up and down. So this distance should be A. This distance should be A. This distance should be A. And it'll go back down and be back down at F. That's down here with again the distance A. If I were to connect the points, it's making a sinusoidal wave. It's making a wave. Now, in simple harmonic motion, there's no resistance or anything to stop it from going forever. Which is physically impossible. But it does give us an idea of what's happening. And we can measure the position of these using either a sine or cosine graph, because they both look like that wave. We can have an A sine, they call it omega t, or a cosine omega t, where S of t is its position up or down at time equals t. omega. It's like a curly W. It's omega, like alpha and omega. What that's called. So our period would have for both of these 2 pi over omega. And since we're doing this with related to time, we have something called frequency. Frequency is 1 over the period, or omega over 2 pi. And what this is oscillations per time unit. So let's look at an example using that 10 centimeter. So it's pulled down 10 centimeters and released. One complete oscillation. Takes 5 seconds. Let's come up with 2 equations that model this. Come up with a sine equation and a cosine that model this. If it helps you, let's plot that on a graph. Let's make the neutral position our 0. And when we start, it's pulled down 10 centimeters, so -10. Starts here. And 5 seconds later. It's back here again. Which means at the halfway mark, or like 2.5 seconds. It's up at the top. And it's following a wave-like motion, so I'll do. This is 0 and 5. And this is 2.5. I need marks for here and here. Halfway between 0 and 2.5 is 1.25. And halfway between 2.5 and 5 is 3.75. Which means the zeros should be at those points, 1.25. And 3.75 should be just under 4. So it's doing some shit like that. If we plotted its position over time, it's doing some stuff like that. And it would keep going. I'm not going to draw it to the left because it starts at time equals 0. So nothing to the left. We release the weight at t equals 0. I think the easiest one to start with here is the cosine. This looks like an upside down cosine, right? Upside down cosine. So my amplitude is going to be where it starts, -10 cosine. We need to figure out what we put in for omega though. Omega is going to be the same for both. We know the period is 5 seconds. That's one complete oscillation. But that should equal 2 pi over omega, which is the equation for the period. So if I solve for omega, multiply both sides by omega. I get 5 omega equals 2 pi. Divide by 5. And I get omega equals 2 pi over 5. Or 2/5 pi, if you like it like that. I like 2 pi over 5. That's my omega. That's what I'm going to put in there for that. Now, if I wanted to do the sine one, looking at the sine would start here, like a normal sine wave goes like this. So my first 0 is right there. That's where I'm going to start my sine. And that looks like it has shifted over. $1.25. If I started there, it's starting a normal thing, and I could do y equals a positive amplitude. My omega hasn't changed. But I need to think about what I'm going to put in there for my phase shift. So I'm gonna do this down in red down here. If my phase shift is 1.25. That's like my H. I should be doing B times X minus 1.25. Where B is my omega. 2 pi over 5. So this is my B X minus H form. On a spring or something like this, we use omega X minus H. So I could do that. I could put it in parentheses and do T minus 1.25 and leave it just like that. Or I could multiply it through. 2 pi over 5 times T minus 1.25 gives me 2 pi over 5T minus 2 times 1.25 is 2.5. And on bottom I have 5 pi, which should just be 1/2 pi, right? So I could write this as y equals 10 sine of 2 pi over 5t minus pi over 2. Let's see if this makes sense. I think that it's gonna work, but let's plug in some values for t and go, does this work? If I let t equal 0, what should this equation equal? At t equals 0, I've got the t part goes away, I have sine of negative pi over 2. What's sine of negative pi over 2? You're going backwards pi over 2, which is 90 degrees. What's sine of 90 or negative 90? Negative 1. So this part, when t equals 0, this part is negative 1. I multiply by 10, and I get negative 10. At t equals 0, I've got negative 10. That looks good there. Let's check at t equals 2.5. Let's just make sure we're up at positive 10 and t equals 2.5. So if t equals 2.5, I've got 2 times that over 5 pi minus pi over 2. This is just 5 over 5, which is just 1, right? So I've got pi minus pi over 2. On the inside of the sign is pi over 2. So at t equals 2.5, sine of pi over 2 is 1. And we multiply by 10 and we're up to 10, so that's tracking there as well. So at t equals 0, we got y equals negative 10. And at t equals 2.5, we got y equals positive 10. That looks like that's a valid equation. And we already did the cosine down here. You might ask, okay, so what else can we do with this? Who gives a shit? Well, if it matters, we could figure out like. How high is it? Shit. Where is this? Where is the weight? When t equals 2 seconds. Now we've got an equation, it doesn't matter which one we plug it into, it should work. Y equals -10 cosine 2 pi/5 times 2. That's my t. So -10 cosine of 4 pi/5. I don't know what that is, so I'm gonna use a calculator. Cosine of 4 pi/5. Parentheses. And make sure I'm in radians. And then I multiply that by -10. I get y equals approximately 8.1. And this was in centimeters, so centimeters. Does that look about right on our graph? At t equals 2, we're right here. So that's a little bit below 10, that looks about right. Assuming I had a better graph, like I drew better. And we can find the frequency. So frequency is 1 over the period. Or 1 over the 2 pi/5. Which is 5 over 2 pi. Which looks weird. Wait, nope, that's wrong. Let's do this the other way. Let's do, because that's not the period. It is 1 over period. But that's omega over 2 pi. So my omega is 2 pi/5. And I multiply that by 1 over 2 pi. And I get 1/5. Now, this was in terms of seconds. My period was in seconds. So it's 1/5 per second. That's probably not all that helpful. Let's think about it in terms of minute. Because that's pretty fast, like measuring the thing in seconds. If I go to minutes. 1 second over 5 multiplied by 1 minute over 60 seconds. Something's off here. The frequency should be higher. Fuck am I doing wrong? No, seconds is on bottom here. That's the problem. The period is in seconds. Period's in seconds, so when I flip seconds over, seconds is on bottom. That's what's wrong. This is upside down. So this gets me 12 per minute. Which is 60 over 5. So it's going up and down a full set 12 times per minute. Up and down and back up. Well, no. Up and down 12 times per minute. Frequency is something you guys know a lot. You may not think of it as much. Your FM radio. Or AM, but FM stands for frequency modulation. Or modulator, I forget which one, I think it's modulation. FM. That number you're tuning into, 101.5 or whatever the fuck it is the frequency. Sound travels in a wave. So radios pick up different stations. Based on the frequency they transmit at. Like your radio, your antenna on your car radio. Radio antenna. It's getting hit by sound waves that are like this. It's getting hit by sound waves that are like this. It's getting hit by sound waves that are super slow. And ones that are super fast. And so what it does is it sets it so that it only picks up the frequency of one of these, ignores all the other frequencies. Because all those radio waves are there all the time, and you don't have a bunch of fuck ups, and so it picks out one of these. Picks out the one you're tuned to. Ever have it where your radio station is fucking picking up two fucking songs? It's always a station that's really close to yours and something's fucking up their transmission or wherever your position is making it so that they're both hitting yours at the same frequency when they're not supposed to be. That's why you every once in a while you get a couple songs on the radio playing at the same time, you're like, fuck, they're ruining a good song. That's what's happening. Alright, so something else that happens in real life that's normal stuff is called damped harmonic motion. And we're not gonna do anything with this, I just want to show you what it is. Damped harmonic motion addresses things like friction. Loss of energy for other reasons. And this is why if you were to do the spring, eventually it slows down and gets to balance again, right? It's not gonna keep going forever. The only way it really modifies this is we put an e to the negative t in front of our functions. The graph of e to the negative t is like this. Never hits 0. But if t equals 0, this equals 1. So when E is 0, this is 1, and as T goes on, this amplitude goes down. Cause we're ignoring the left half of this graph, it starts at T equals 0. This is our amplitude. And the amplitude is decaying with time. And that's why it starts off strong, but it slowly or quickly gets down into not doing shit. And that just depends on the frequency and stuff like that. And now you learned a little physics and what triggers, some of the stuff triggers good for. I'm done with this. This is not on the test, it's just to give you a little flavor of what's going on. GTFO, have a good day. We're doing the group practice test on Wednesday, come in. Be prepared.